All right, section 2.5, continuity. This is a pretty important section. There's a little bit of a lengthy section. There's a lot of things to talk about in this section, but continuity is an extremely important issue as it relates to some of the other topics that we're going to deal with in calculus. And so it's one of those kind of things that, once we establish what exactly continuity is, what that means, then a lot of things that we're able to do in calculus are dependent upon functions being continuous, right, or continuity being present. So it's one of those things that's always kind of working in the background, so we don't want to forget about it. We don't want to take it for granted, right? So yeah, so there's a lot in this section. So it's a little bit longer than some of the other sections that we're looking at. So we'll get to it. All right. So continuity. What do we have? We say that a function f is continuous at a, or at a number a, if the limit as x approaches a of f of x equals f of a. And while I'm thinking about that, because I stumbled on it already, continuous at a number a. Right, notice I always underline that a when I'm talking about the a value in terms of our limit. Right? So when we say our number a, not to confuse that with the word a. Right? So a function f is continuous at a number a if the limit as x approaches a of f of x equals f of a. Right, so we're saying essentially then the value of the limit as x approaches a is equivalent to the function value at a, right, f of a. Now there's actually three things involved there in that single statement. So three requirements for a continuity at a number a. First of all, f of a has to exist. Right? A has to actually be in the domain of our function. That's always the first thing you check. If I have a value that's not in the domain of our function, then our function cannot be continuous there. So always check that first. Second, if a is in the domain of the function, you can plug it into the function and get an output. Then we check the value of the limit as x approaches a. So we then need that limit to exist. Right? Now just because a is in the domain of our function doesn't mean the limit as x approaches a exists necessarily. Right? So we check to see that limit exists. Then we get to the final statement that if those two values exist and they are the same, then your function is said to be continuous at the a value. All right, so then otherwise it's discontinuous. So otherwise we'll say that f is discontinuous at a if any of those three requirements aren't met. So anytime you're having a discussion about continuity, is this function continuous at a number? Is this function continuous over an interval? You're always going to fall back upon these three requirements. It's a checklist. First of all, is the function defined at the value? Second, is the limit as x approach that value exist? And third, are those the same? And if those three can be checked off as true, then you have continuity at that point. Otherwise, you have discontinuous or discontinuity. Graphically, all right, so and I'm going to do this two different ways. We'll look at it graphically, then we'll also bring in some actual functions and do the mechanical work with it. So graphically, this is what it means to be continuous. And we've always, we maybe mentioned continuity before. If you're drawing a graph of a function, for that function to be continuous over whatever part of the graph you're drawing means that you should be able to put your pencil to paper, draw the entire graph without picking your pencil up. Any point at which you have to pick the pencil up in order to continue to draw the graph is a point of discontinuity. So that's the easiest way to tell where, if you have a point of discontinuity on the graph of a function. So if you look at the examples that I have in this particular graph, right, we've got a function that's discontinuous at this point. There's a hole in the graph. So I have to pick the pencil up to draw the graph of that function at that point. Now, in terms of justification, and you will be asked this, right, why is it discontinuous at that point? Well, the first requirement is that the function is defined at that a value, or at that, in this case, at 1. And this function value does not exist, right? 1 is not in the domain of our function. So I would say that this function is discontinuous at 1 because f of x is not defined there. There is no point on the graph that corresponds to f of 1. The second situation where we have discontinuity, right? We draw our graph, we get to this point, and then we have to pick the pencil up again to get to that point. Also notice too, again, at the bottom there's a closed point, at the top there's an open point. They can't both be closed. That would violate vertical line test for a function. So only one of those can be a closed point to actually have a function. But again, I have to pick the pencil up to draw the graph. Now, why is it discontinuous there? Well, that has to do with the limit. Because notice the first requirement, the function has to be defined. Well, it's defined down there at the bottom. There's a closed point here. So I've got a f of 3 is defined. But the limit as x approaches 3 does not exist. Why does that limit not exist? Because as we approach 3 from the left, our function is approaching whatever that y value is. As x approaches 3 from the right, it's approaching whatever that y value is. All right, so that goes back to our limit discussion, in that I can tell you there that the limit as x approaches 3 does not exist, because as we approach 3 from the left and from the right, the graph is approaching 2 different points. Okay, so that's our second requirement. So I would then say that that function is discontinuous at 3 because the limit as x approaches 3 of f of x does not exist. We call that a jump discontinuity. That's the more formal word for that. Because if you're drawing it, think of it this way, if you're drawing the graph, you have to jump from that bottom piece to the top piece, right, in order to continue to draw the graph. So that's called a jump discontinuity. The third situation where we have a point of discontinuity is at 5. All right, so again, first requirement, does f of 5 exist? Yes, it does. There's a point right there. That's my function value for 5, whatever that y coordinate would happen to be. But f of 5 exists. There's a point on the graph whose x coordinate is 5. Does the limit as x approaches 5 exist? Again, yes, it does. Because as we approach 5 from the left, as we approach 5 from the right along our graph, we're approaching the same point. Okay, now again, remember, for the evaluation of the limit, I don't have the point there. I don't care about what happens at that point. It's all about what the graph is approaching. Same. So f of 5 is this, whatever that value happens to be. But the limit as x approaches 5 is this, whatever that happens to be. So those two values are not the same. So that's our third situation where even though the first two requirements are met, they're not equal to each other. So in this case, I would say that this function is discontinuous at 5 because the limit as x approaches 5 of f of x is not equal to f of 5. Okay? So that's a graphical observation, and it's pretty easy to tell, like I said, if a function is discontinuous or not continuous at a point, because you can very easily see on the graph there's either a big gap like you have here, or there's one of those holes in the graph like you have there. But then again, if I need to give the reason, I need to understand why. I can't just say, well, there's a hole in the graph. Well, what does that mean? There's a hole. Now, while I'm thinking about it, I'm going to go back and mention this. I can't just say that it's discontinuous because there's a hole in the graph. Because I have a hole in the graph here, I also have a hole in the graph there. But the reason for discontinuity is different in each of those two situations. I also have a hole in the graph there. All right? So there's a hole in the graph at each of those three different locations, but the reason for discontinuity is different. Right? So it's not sufficient to say, well, it's discontinuous because there's a hole in the graph. You need more than that. All right, so it always goes back to those three statements. Either the function value does not exist, or the limit does not exist, or if they both exist, they're not the same. All right, the next set of examples has more specific problems. Here's some specific functions that we're looking at. And we're determining at which values is the function discontinuous and why. All right, so the same as we did in the graphical example, but here we're just going to do it more in terms of the actual function. So the first example, that should be the most obvious. If I look at the function f of x equals x squared minus x minus 2 over x minus 2. All right, that's a straightforward rational function which is undefined when x equals 2. All right, so I can tell you that that function is discontinuous at 2 because f of 2 does not exist, right? Or f of 2 is undefined, or 2 is not in the domain of f. Right, so something to that effect, but it has to do with the fact that that function is undefined for x equals 2. The second function, part B. Here's a piecewise function. We love piecewise functions. Opens up a lot of different single functions. So this part B piecewise function, I've got two parts here. I've got f of x equal to x plus 4 for values of x that are less than or equal to negative 2. And I've got f of x equal to x squared for values of x that are greater than negative 2. Now, we're going to get into a little more discussion here in this section in terms of, well, the only point I'm really interested in here is negative 2, where that function is broken. And, why do I not have to worry about everything else? Well, we can talk about the graph first of all. I mean, if you look at the graph of x plus 4, that's a basic little linear function. That's a line, right? I can draw the line without ever picking up my pencil. So I know that the function is continuous for every value of x in that part of the function, which is less than or equal to negative 2. Likewise, I know this function is continuous over this second interval for x values greater than negative 2 because our function is x squared. That's a basic quadratic. Again, you can draw the graph of the entire parabola without ever picking your pencil up. So certainly over the interval for x greater than negative 2, this function is continuous. So the only point of contention is at this breaking point where x equals negative 2. So we have to show either the function is continuous there, or if it's not, why? So we go through the checklist, okay? What's the first requirement? In order to be continuous at negative 2, the function has to be defined at negative 2. So is negative 2 in the domain of our function? Absolutely. Right there it says less than or equal to negative 2. So f of negative 2 exists. Check. Second requirement, the limit as x approaches negative 2 has to exist. Well, here we definitely have to deal with the left and right hand limit because we're looking at two different definitions of our function. This definition for values of x less than negative 2, so as we approach negative 2 from the left. And this definition for x values that are greater than negative 2, so as we approach negative 2 from the right. So in order to evaluate the limit as x approaches negative 2, we have to go back to our one-sided limits, right? Because we do have two different definitions for our function depending upon which side of negative 2 you're coming from. So for the left side, so now again, and you see everything I have written here is exactly what you would have to write, to justify your observation. So I've got the limit as x approaches negative 2 from the left of f of x, lost a parentheses there, would be equal to the limit as x approaches negative 2 from the left of x plus 4, because that's our definition of the function on the left side of negative 2. And then I can use direct substitution as we approach negative 2 from the left. And we said direct substitution works for one-sided limits. I can plug negative 2 in, I've got negative 2 plus 4 or 2. And so that would be the limit as x approaches negative 2 from the left. And then we repeat the process for the right side. The limit as x approaches negative 2 from the right of f of x, right, so that's those values greater than negative 2. Our function there is defined by x squared. So again, then I'm using direct substitution. I can plug in negative 2 squared, I get 4. And that would be our limit as x approaches negative 2 from the right. And so then based upon these two, I can tell you that the limit as x approaches negative 2 does not exist. Why does it not exist? Because the limit as we approach negative 2 from the left and the limit as we approach negative 2 from the right are not the same. Right? They're not equal to each other. So that's our second possibility. So back over here, there's my justification for discontinuity at negative 2, because the limit as x approaches negative 2 of f of x does not exist. Part C, there's another piecewise function. I've got f of x equals x squared minus x minus 2 over x minus 2. Remember, notice that was part A, same function there. And the problem with part A was, right, our function was not defined when x equals 2. So the function was discontinuous there. So what I've done is I've given the function a value when x is equal to 2. So we have the same function, that's our function when x is not equal to 2. We know 2 is not in the domain of that function. That's fine. So let's put it in the domain of our function by saying if x equals 2, the function value is 1. All right, so we're going to have the same issue similar to what we had before, right? You think of the graph of your rational functions, where you have horizontal asymptotes, that kind of thing. You can draw the graph without picking your pencil up until you hit those, I should say vertical asymptotes, not horizontal. You can pick until you hit one of those vertical asymptotes, and then you have to pick your pencil up. Now again, we're going to get into more detail as we go through this section, so I'm kind of bypassing a lot of the specifics here. But we do have a function, just like in part A, that is continuous everywhere except at 2. And then by filling in this piece of the function, I now have a function that is defined at 2. So that takes care of part A, or the first requirement. So then we have to look at our limit, right? What is the limit as x approaches 2? And does that exist? And so this is one of those cases where if you look at that limit as x approaches 2 of f of x, I'm looking at the limit as x approaches 2 of x squared minus x minus 2 over x minus 2, because again, I don't care about the second part of this when I'm evaluating that limit, because I don't care about what happens at 2. It's all about what happens as we approach 2. So I'm looking at the limit as x approaches 2. I can't use direct substitution, but here's a case where we can rewrite the function. We said that's one of our tools that we have at our disposal. If I'm trying to evaluate a limit and I cannot use direct substitution, can you rewrite the function into a different form that allows you to use direct substitution, right? So here, if I factor the x squared minus x minus 2, we can divide out the common factor of x minus 2, and I have equivalently the limit as x approaches 2 of x plus 1. All right, now remember what we said about this, because I don't want to forget this observation. Remember, we're saying these two functions are not equivalent. This is a simplified version of this one. They are exactly the same everywhere except at x equals 2, right? Because that function on the left is undefined when x equals 2. This one is defined when x equals 2, right? So they're not the same function exactly, but they are exactly the same everywhere except at 2. And that's fine in terms of the limit, because if we're evaluating the limit as x approaches 2, I don't care about 2, right? So as long as we include this limit statement, then now these two statements are exactly the same. The limit as x approaches 2 of x minus 2 times x plus 1 over x minus 2 is exactly the same as the limit as x approaches 2 of x plus 1. So I'm re-emphasizing that because that tends to get lost, right? Without that limit statement, those two functions are not equal to each other. But the limit statements are equal to each other. But then after simplifying, right, this is what the whole purpose for that was. Once I do simplify the function, I can then plug 2 into it. I can use direct substitution, and I get 3. And so that's the value of the limit as x approaches 2. Okay? But then the problem here is, the third requirement is that the first two have to be the same. Right? So f of 2 equals 1. That's by this definition, right? When x equals 2, f of x equals 1. So f of 2 equals 1. But that's not the same as the value of the limit as x approaches 2. So we do have the function defined for x equals 2. We do have a limit that exists as x approaches 2, but they're not the same. So that's that third requirement, or that third situation. Right? So this function would be discontinuous at 2 because the limit as x approaches 2 of f of x is not equal to f of 2. So what if I fixed that? The problem is that those two are not the same. So notice I have that part D over there on the left margin that I scribbled in. What if we change this to that? Now, when x equals 2, f of 2 equals 3. And if f of 2 equals 3, then we now have continuity at 3, right? Because now that limit as x approaches 2 is the same as f of 2. And this function then would be continuous everywhere. Okay? We call that a removable discontinuity. Now, remember I mentioned that jump discontinuity earlier when you were drawing the graph and you had to jump from point to point. This is called a removable discontinuity, because if you draw the graph of this function, there's going to be a hole in the graph. I lost my bar there somehow. there's going to be a hole in the graph at x equals 2. But then what you can do is you can define f of 2 to equal 3, and it's going to fill in that hole. Right, so that's a removable discontinuity. I don't have my graph to refer to. Oh, yeah, this one. So it would be a case like this. That's a removable discontinuity, but instead of my point being up here, I can fill in that there. That's what's happening. Okay. Not super critical, but it's sufficient to say that it's a point of discontinuity. You don't have to specify whether it's a jump discontinuity or removable discontinuity. That's for additional classification should we need to make that observation. Next, definition. A function f is continuous from the right at a number a if the limit as x approaches a from the right of f of x equals f of a, and f is continuous from the left at a if the limit as x approaches a from the left of f of x equals f of a. So this is the same definition that we had previously, where the previous definition talked about the overall limit, right? The limit as x approaches a of f of x equals f of a. Well, what if my function is not continuous at a because maybe the limit doesn't exist? Maybe the limit from the left and limit from the right are not the same, and that's the reason for discontinuity. Well, then maybe we can talk about the function being continuous from the left or continuous from the right if the function value agrees with the one-sided limit, right? So if f of a, and again, notice too, first and foremost, the function has to be defined, right? F of a has to exist, and that's why we always check that first. Is that a value in the domain of our function? If it is, then we move to the limit statement, right? So then if the limit does not exist, and the reason for that is the left and right hand limit are not the same, if one of those limit values does exist and happens to be the same as the function value, then you do have continuity from the left or continuity from the right. Right, you still don't have continuity at the point overall, but you can have one-sided continuity, right? So it's just like when we talked about the limit in general, right? You can have an overall limit that exists, but you could have a limit that does not exist, yet have a limit that exists from the left or from the right. So it's the same idea in terms of continuity. Definition: a function f is continuous on an interval if it is continuous at every number in the interval. That should reasonably make sense, right? So whereas before we were talking about continuity at a point, at a single value, here we're talking about continuity over an entire interval, right? So maybe an interval between a and b. So it's reasonable then to say, of course, it would have to be continuous at every number, every point in the interval. But then there's a second piece to that. You can also then talk about the end point of the interval. So we're going to have to be continuous at every point in the interval, obviously, but is it continuous at the end point of the interval, whether it's the end point on the left side or the end point on the right side? Okay, so if f is defined only on one side of an endpoint of that interval, then continuous at the endpoint means either continuous from the right or continuous from the left, and that'll just depend upon which endpoint you're on. All right, I'm going to give you an example here in a second, but here's the basic idea. Let's say I've got a function, all right, that's continuous over some interval from a to b. Okay. Continuous at a means, in this case, that I would be continuous from which side? From the right. A is the left boundary point of that interval, but continuity at a means I'm looking at the limit as x approaches a from the right side being equal to f of a. And then just the opposite would be true for b. This would be continuity from the left, because f of b, whatever that value happens to be, would be the same as the limit as we approach b from the left side, but b is the right endpoint of our interval. That I think just sometimes throws people off, I don't, just because of the whole right-left thing. So remember, when you're evaluating a limit and when you're talking about continuity, It's all about which side you are approaching that point from. All right, so not which side of the interval is it located, but from which side, if you were following the graph of that function, from which side would you be approaching? Okay, so that would be continuous from the right at A. It would be continuous from the left at B. But I see issues with that sometimes. It's, I guess, just the visual of the end points of the interval versus which side you're coming from. So here's a specific example from the graph of f. Determine where f is discontinuous. And then for each of those numbers, state whether f is continuous from the left, from the right, or neither. Okay? But the same definition applies as before. If I have a point of discontinuity, and again, first of all, it's pretty obvious to tell from the graph, we already said. But then, can I justify or clarify, do I have continuity from the left or from the right? Possibly. Or still neither. I mean, it could be still continuous from neither side. So if we look at our graph, if you look at this first point of discontinuity, all right, and again, we keep saying the very first thing you always check for when you're talking about continuity is that point or is that number in the domain of your function? And in order for that point or that value, in order for -4 to be in the domain of that function, there has to be a point on the graph whose x-coordinate is -4. And there's not in this case, right? There's a hole in the graph. So this function is discontinuous at -4. Now, is it continuous from the left or continuous from the right? Well, again, that would be neither, because -4 is not in the domain of the function. There is no point. I don't care how you approach it. You can approach from the left side, you can approach from the right side. There is no point on the graph whose x-coordinate is -4. So that would be continuity from neither side, or it would be discontinuous from both sides. Now, when you get to this next point at -2, that's again, first question, is -2 in the domain of the function? That is, in this case, because I've got a point right here that has -2 as its x-coordinate. Now, what does that value of the function agree with? It agrees with the limit as we approach from the left. Right, so as we approach -2 from the left, the limit as x approaches -2 from the left would be the same as f of -2. As we approach -2 from the right, we're approaching this point. But that's an open point. There's no function value there for -2. So that's why we said earlier, which side are you approaching from? Okay. So basically, if you're looking at one of these jump discontinuities, which piece has the closed point? And then whichever side you're approaching from to get to that point, that's the direction of your continuity. So I would say that this function is continuous at -2 from the left, because as we approach -2 from the left, we're approaching that function value. Let me go over here. There's our -4 neither, and there's our -2 from the left. The next point of discontinuity, it's another jump discontinuity at 2. But in this case, the open point is here, the closed point is there. So when I look at the function value for 2, f of 2 is up here, which would agree with the limit as we approach 2 from the right. The limit as you approach 2 from the left would be whatever this value is, but there's no point there. Okay. So f is discontinuous at 2, but it is continuous from the right. And then the same thing happens at 4. All right. Now in this case, I just have the left side of this thing is shooting off on the left side of 4 as x approaches 4 from the left. Right, our limit is -infinity. Remember, we said the limit does not exist, but we could describe it by saying the limit as x approaches 4 from the left is -infinity. The limit as x approaches 4 from the right is whatever that point is, which is exactly the same as f of 4. Right, so there's our right side limit. As we approach that point from the right, that limit is equivalent to the function value at 4. So we do have continuity from the right. This next little example may seem a little bit trivial, but it's an example of kind of like a proof type situation. It kind of just emphasizes again that definition of continuity and what does it mean to prove or show continuity, right? So it may seem a little bit trivial or I don't know, kind of redundant in what it's saying, but it is a perfectly good example to prove continuity, in this case, over an interval. So we're showing that our function g of x equals 2 times the square root of 3 minus x is continuous on the interval from negative infinity to 3 inclusive. All right, so continuity first thing, and again, we're showing it, we're not asking it, we're showing it. So we want to prove that this is a true statement, that it is continuous on that interval. So we always start for continuity with the first requirement: the function has to be defined at every point in the interval. So the interval from negative infinity to 3, if I look at that function, 2 times the square root of 3 minus x, maybe I'll go over here and remind us, when we're looking at the domain of this function, here's another quick algebra review. What's the domain of that function? How do you determine the domain of that function? Well, it's a square root function, and for a square root function, we know that the radicand cannot be negative. Right? The radicand has to be greater than or equal to 0. So for any square root function or even index, that's how we find the domain. We take the radicand, set it greater than or equal to 0, and then we solve it for x. So I'm going to subtract 3, divide by negative 1. Remember, when you divide by negative, reverse the inequality. So there's the domain of that function. X is less than or equal to 3. So as long as we have values in that interval, right, negative infinity to 3, they are in the domain of that function. So that meets the first requirement, at least for that specific interval, right? So check. Second requirement, we have to look at the limit as x approaches a of our function. Right? And again, this a value could be any a value in that interval from negative infinity to 3. All right, so because of that stipulation. So we do have the limit then as x approaches a of 2 square roots of 3 minus x. And I broke this down using the limit laws. All right? But you could really kind of, if you wanted to use direct substitution here, because we said as long as it's in the domain of the function, we haven't mentioned radicals yet. But that's going to be true also. So I went through the limit laws and broke it down step by step there. But essentially, it's still direct substitution, right? If I plug a in place of x, I have 2 square roots of 3 minus a, which notice that's exactly the same as g of a. Right? I just plugged a into g. And that resulted from the limit as x approaches a of our function. So therefore, I could say that g is continuous on this interval because the limit as x approaches a is equal to g of a, provided, like we said, we have a values that are less than or equal to 3. I'm not going to ask you to do anything like that on a test. It's kind of just an illustration of how we can use that definition for a broader application. Instead of just a single value, I use it to show that we have continuity over an entire interval. A few theorems to mention. This first theorem, again, kind of straightforward. It's similar to what we talked about with limits, but we do want to make sure we're clear. Like I said, you never presume or assume any of this stuff without first proving it or showing that it is actually true. So this theorem tells us that if f and g are both continuous at a number a, and c is a constant, then the following functions are also continuous at a. The sum, difference, product, and quotient of our two functions, as always, provided the denominator is not 0, and also a constant multiple of our function. So in other words, if I have a function f and a function g that are both continuous at some value, then their sum is also continuous there, their difference, their product, their quotient, and any constant multiple of either of those functions would also be continuous at that point. Okay. These next two theorems kind of go together. The second one is an extension of the first one. The first one says that any polynomial function is continuous everywhere, or in other words, it's continuous on the entire set of real numbers. And that goes back to, we talk about the graphs of those functions, polynomial functions. The domain of every polynomial function is a set of all real numbers. You don't have any gaps or holes or asymptotes or anything like that on the graph of a polynomial function. So they're continuous everywhere. We've already mentioned rational functions. We did a couple of examples with those, like with those piecewise that we looked at earlier. Any rational function is continuous everywhere that it is defined. So in other words, it's continuous on its domain. All right. So that's a theorem, great, fine, wonderful. It actually gets caught up in the next theorem as well. That gives us a list of functions that are continuous over their domains. All right. So this bypasses all that other discussion we had to have earlier, about the graph and can I draw the graph without picking up my pencil and all that stuff. This is a more specific description of that, in that provided or whatever the domain of the function is, it's going to be continuous over its domain, right? And so it's only going to be discontinuous at values that are not in its domain. So this statement is true, this theorem is true for polynomial functions, as we just mentioned, for rational functions, as we just mentioned, right? So we just mentioned those previous two in the other theorem. But this is also true for root functions, like the one we just looked at. Also true for trig functions, also true for inverse trig functions, exponential functions, and our log functions, right? And those are basically all the function types that we work with. I mean, there are other types of functions, but these are primarily the types of functions that we work with in most cases. So we can say that every one of those types of functions is continuous over their entire domains. Which actually then leads us into the most important statement here, that one at the bottom. If a function is continuous, then the limit as x approaches any of its domain values can be found using direct substitution. So this combines the whole limit and continuity thing, all right, those two concepts, in that if a function is continuous at a number, I can evaluate the limit as x approaches that number simply by using direct substitution. And that, it's a case where that may seem a little bit obvious, but like we keep saying with that stuff, you cannot presume or assume anything. Everything has to be proven. Now, once we prove that it's true, then yeah, we can do it. Okay? But you can never take any of this stuff for granted. If it's not a statement that's been proven to be true, so any of you that are, if you're heading into like higher levels of math, depending on what your majors are, and these higher levels of math, this is what you end up doing a lot of, is having to deal with situations where, okay, I don't have a specific statement regarding this, so then I have to go through and prove the observations that I need to make. So you end up doing a lot of proofs and verifying that statements are true. Okay? Just simply because you can't take anything for granted. Next theorem. Right, we do love our theorems in calculus. If I didn't mention that before, I'll mention it again. We love our theorems because theorems are like laws. Once somebody proves something to be true, then it becomes a law, then it becomes a theorem. And that means we can use it as a tool in other situations. Right? So we love our theorems, things that are proven to be true. So this next theorem says that if f is continuous at b, and the limit as x approaches a of g of x is equal to b, then the limit as x approaches a of f of g of x equals f of the limit as x approaches a of g of x, which is equal to f of b. And what is that exactly saying? All right. Remember, what is this? That's composition of functions. Remember that from algebra. Composition of functions, f of g of x, where I take g and I plug it into f composed with g, if you want to use that language. So what this theorem is allowing us to do is evaluate the limit of a composition of functions. And again, it gives us a way to break this thing up. If I look at the composition of the two functions, if I look at this f composed with g, and the function that I have there is either very difficult to work with or maybe impossible. Maybe that limit can't be evaluated. Then I could possibly look at composing f with the limit as x approaches a of g of x. So in other words, the limit of f of g of x can be evaluated possibly by taking the composition of that outer function and the limit as x approaches a of that inner function. Because maybe I can evaluate this limit, just the one involving the inner function. And if that limit exists, and then I have a number that comes out of that can be plugged into f, right? It happens to be in the domain of f, then I'll simply do that. I'll take the composition of f and that limit value. Now again, as with all theorems, sometimes the examples kind of make it easier to understand exactly what the heck the theorem is saying. So if the wording in the theorem confuses you, that's understandable. And then we can kind of take that now and put it in the context of an actual example or a specific problem, and see how that works. And then maybe that'll help to clarify exactly what that theorem is saying. Now, I haven't mentioned this before. I think I'm not going to ask you to regurgitate any of these theorems to me on a test. I'm not going to ask you, what does this theorem say? What does that theorem say? No. You need to know what the theorems say in order to use them. But I'm not going to ask you to spit back to me all these different theorems. Absolutely not. But you do have to know what they say in order to properly use them. So for example, let's evaluate. Find the limit as x approaches 1 of the inverse sine of 1 minus square root of x over 1 minus x. So a couple of different things to deal with first there. We're dealing with an inverse trig function. Not always the favorite type of function to work with. Trig functions, much less inverse trig functions. But the first thing we always have to deal with any of these theorems, remember, is continuity. Right? If you look at that theorem, if f is continuous at b, and that limit exists. So we have to have continuity of the outer function with respect to whatever the value of the inner function is. So we start with our continuity of the outer function, the inverse sine. It is continuous. It was on that list that we just gave you, right, in that theorem of functions that were continuous over their domains. Well, here's a question from trig. What is the domain of the inverse sine function? How many trig questions do we have to go back and review? Right? And I keep telling you, it's not going to be the calculus that causes most of your problems. It's going to be algebra and trig that cause a lot of the problems that you have with this stuff. So first of all, just here's a quick review. What's the domain of the inverse sine function? Well, remember, the inverse sine function has a domain that is the same as the range of the sine function. Remember, inverse functions, domains and ranges are reversed. So whatever the domain of the inverse sine function is, it would have to be the same as the range of the sine function, which is negative 1 to 1. Now the range of the inverse sine function, and again, this is for review purposes, because once we do evaluate this thing, I have to know what my outputs would be. And remember, from trig, we spend a lot of time talking about these inverse trig functions, and there's a lot of details that can be misinterpreted or forgotten. And if you remember, in dealing with inverse trig functions, in order to define an inverse sine or inverse cosine or inverse tangent function, you had to first restrict the domain of the trig function itself. And that had to do with all that one-to-one function stuff. So if you need to go back and review some of that in your trig, all right, that's in chapter 7, or that would be 7.4. If you go back and look at your trig notes from previously, then you should have all your discussion of the inverse trig function. But for our purposes, right, we at least need to know what the domain and range are. Because when you evaluate an inverse trig function, you're only going to get values that are in its range. And the restriction that we had to put on the domain of the sine function, which then becomes the range of the inverse sine function, is we said it had to be angles between negative pi over 2 and pi over 2. For inverse cosine, the domain is the same as the domain of inverse sine because sine and cosine have the same range, negative 1 to 1. But the range of the inverse cosine, which is the restricted domain of cosine, is 0 to pi. For inverse tangent, domain is all real numbers. That's the range of the tangent function. The range of the inverse tangent is negative pi over 2 to pi over 2, but notice in this case not inclusive, right? We include the endpoints for the sine function, inverse sine, excuse me, but we do not include negative pi over 2 or pi over 2 for the inverse tangent because tangent is not defined there. So that's why, and those of you that took trig with me, y'all know, I mean, we asked you repeatedly, right, continuously, what was the domain and range of those functions? Because I wanted to hopefully that to stick, so, you know, because we do work quite a bit with trig functions in calculus, and so you at least have to remember the domains and range of those things. And those basic function values, you know, your values for pi over 6 and pi over 4 and pi over 3 and those quadrantal angles, you know, pi over 2 and all those. You have to know those basic values because those are the ones that are going to come up in the context of evaluation of trig functions and inverse trig functions. Okay, so that's kind of an aside. That's just a quick review, and as I said, if you need to go back and look at some of that again, review that from your trig, I would advise you to do that. All right, so that takes care of at least continuity part of the outer function, you know, as long as once we go through this process, we are able to plug in a value that's actually in the domain of the inverse sine function. All right, so I have to end up with a value between negative 1 and 1 that I plug in. All right, so then here's the process, here's the theorem itself. So that theorem said that if I have the limit of a composition, I could possibly, and maybe I should even put a question mark here, possibly I could evaluate the composition of the limit. So I took the limit as the inverse sine of that fraction, and we're saying, okay, is this equivalent to the inverse sine of the limit of the inner function? Now this limit that I'm going to evaluate, now we're back to what we did previously. All right, I'm evaluating the limit as x approaches 1 of 1 minus square root of x over 1 minus x. So 1's not in the domain of that function, but that's one of those, remember that little conjugate trick we used? We said if I multiply the numerator and denominator by the conjugate of that numerator, I then end up with, now that's 1 minus square root of x times 1 plus square root of x, so we get difference of squares, which would be 1 minus x. And then the denominator is 1 minus x times 1 plus square root of x, but remember, notice our whole purpose for that rewriting was to hopefully eliminate that denominator, that factor that was causing the problem with direct substitution. So I got rid of the 1 minus x. Now I still have that inverse sign on the outside. Don't lose this guy. I'm evaluating this limit, but the inverse sign is still on the outside of that thing. So now I've got the inverse sign of the limit as x approaches 1 of 1 over 1 plus square root of x, which I can now evaluate that limit using direct substitution. I can plug 1 into that, and I get 1 plus square root of 1, or 1/2. And now I've got the inverse sine of 1/2. Now again, quick review from the trig. What does it mean to evaluate the inverse sine of 1/2? The question is, what is the angle? Because the output of your inverse trig function is the angle whose sine is that. Provided that it is in, this is where this always comes into play, it has to be an angle in that interval. And that's the part that everybody forgets. So I'm evaluating the inverse sine of 1/2. I'm looking for the angle that has a sine of 1/2, and that's where I go back to, like I said earlier, you've got to know those basic trig function values, because the sine of pi over 6 is 1/2. All right, there's a lot of little things that you have to keep keep track of. But that has nothing to do with calculus. That's all about basic trig. So I strongly again advise that you maybe go back and review your basic trig values. All right, know your domains and ranges. Know those function values for those common angles, pi over 6, pi over 4, etc., etc. theorem at the bottom, continuity theorem. If g is continuous at a and f is continuous at g of a, then the composite function f composed of g, or f of g of x, is also continuous at a. So it's another composition of functions, but this in terms of this one with continuity, or with respect to continuity. So in other words, what this says is, if this inner function g is continuous at a, and then the outer function f is continuous at g of a, then their composite function is also continuous. Or in other words, a continuous function of a continuous function is also a continuous function. But as is always the case with these composite functions, you're always working from the inside out. So it has to do with, is the inner function continuous at whatever our a value is? If it is, what is g of a? And then if f, the outer function, is continuous at that value, okay, then our composition is continuous. Right? So again, a continuous function of a continuous function is a continuous function, for what that's worth. Next example, again having to do with continuity of a function. Right? So we're going to have to rely upon our definition. And I said anytime you're asked about continuity, we fall back upon the definition, that three-part requirement for continuity. For this one, we're asked to show that this function f is continuous on the entire set of real numbers. Right? So show that f is continuous everywhere. Well, the first part of this, and we saw this previously with these piecewise functions, it always ends up being about the point where you're breaking the function up. So in other words, if I want continuity everywhere, first thing I can do, I can tell you that it's continuous on the interval from -infinity to pi over 4. Why? Because our trig functions are continuous on their entire domains, which for the sine function is the set of all real numbers, which certainly includes -infinity to pi over 4.
Messenger video.
So my phone's going crazy. So we are continuous over that first interval because of our sine function, and then similarly the second function, or the second part of our function, I should say. All right, so f is also continuous on the interval from pi over 4 to infinity because our cosine function is continuous over its entire domain, which is also the set of all real numbers. Okay. So that just leaves us with, as usual, that point at which we are breaking the function. Do we have continuity at pi over 4? And since now we're dealing with a single point, like I said, we'll go back to our definition of continuity, which has 3 requirements. So the first requirement is our function defined at x equal to pi over 4. And yes, it is. It's right there. Pi over 4 is included in that part of the function, so it is continuous, or it is defined. So f of pi over 4 exists. That's our first requirement. Second requirement, we check the limit. Right? What is the limit as x approaches pi over 4? And because it is a piecewise function, we have to look at the left-hand limit and the right-hand limit, right? Because we have different definitions depending upon which side of pi over 4 we're coming from. So for x less than pi over 4, our definition is sine x. So I can look at the limit as x approaches pi over 4 from the left, would be at the sine of pi over 4, which is square root of 2 over 2. The limit as x approaches pi over 4 from the right, that's our values of x greater than pi over 4. That's defined by cosine of x. So I've got cosine of pi over 4, which is also square root of 2 over 2. So I do have the limit as x approaches pi over 4 existing, and it is equal to square root of 2 over 2. And our first requirement, we said pi over 4 is in the domain of our function. It's in that second piece, so the cosine of pi over 4, which we just said is square root of 2 over 2, is exactly the same as the limit as x approaches pi over 4. Right? But there's our process. Right? I mean, now again, be careful with a question like this because they are asking us to show that it is continuous over the entire set of real numbers. So it's not just enough to show that it's continuous at pi over 4. we also have to make these statements in order to include everything else. Right? So we don't have to do anything to prove that because we already know this is true. So it's sufficient to say that f is continuous on the interval from negative infinity to pi over 4. It's also continuous on the interval from pi over 4 to infinity. And then we have to go through the process to show that it is continuous at pi over 4. So f of pi over 4 exists. It is equal to square root of 2 over 2. Limit as x approaches pi over 4 exists. We just showed that looking at the left and right hand limit. It is also square root of 2 over 2. Therefore, I can say that f is continuous at pi over 4, and then putting all three parts together, I can say then that f is continuous over the entire set of real numbers. The main issue I usually see with that particular type of problem is simply forgetting about the intervals, right? And we're so focused on just that specific point, pi over 4, that we forget to also include the intervals less than and greater than pi over 4. So that has to be included in our statement in order to prove or show that it is continuous over the entire set of real numbers. Okay? Last theorem in this section, the intermediate value theorem, or what we call the IVT. Suppose that f is continuous on the closed interval from a to b. And we're going to let capital N be any number between f of a and f of b. Right, so n is some number between the function values, f of a and f of b, provided that f of a and f of b are not the same. Right, so we want different function values, or have to have different function values here. Then this theorem says that, again, provided your function is continuous on that interval with different or unequal endpoints, then there exists a number c, we'll call it, somewhere in that interval such that f of c is equal to that n value. Okay. Now again, I think it's a situation where if you look at it graphically, it makes perfect sense. But you kind of have to jive that or mesh that with the wording within the theorem and what the theorem says. So what this says basically is, look, I've got an interval from a to b, a closed interval, where my function is continuous over that interval, which means what? We have to be able to draw the graph without picking our pencil up. Right? So over that interval from a to b, I've got a continuous function. That's critical. Now, it's not the main part of the theorem, but it is a requirement in order for the theorem to be true. So here, because here's the thing about theorems too. Anything that the theorem says, if there's certain requirements that have to be met, if those requirements aren't met, then the theorem cannot be trusted, right? Or in other words, the conclusion cannot be verified, right? So in other words, if this function was not continuous on the interval from a to b, then everything else that's stated after that doesn't mean a thing. All right, so you got to be careful again with theorems and what they say, and that there are specific requirements. Those requirements have to first be met in order to validate the conclusion. Okay. So this function is continuous on the interval from a to b, provided that f of a is not equal to f of b, which we have in this case. I've got two different endpoints. One, there's f of a and there's f of b. Then we're saying that within that interval from f of a to f of b, if you pick a number n within that interval, somewhere between these two guys, we guarantee you that there has to be a number c such that f of c is equal to that n value. Okay? And so basically what you're saying is, I'm picking a point, a function value, somewhere between f of a and f of b. And for any function value that you pick between those two, I absolutely guarantee you that there has to be an x value that produces a y value between those two. But it's all based upon the idea of continuity. If you don't have continuity, then that's not necessarily true. Now, whoop-de-doo. What's so great about that? Here's an example of where something like that can be used. And a context for something like this, a broader application of these types of situations. Sometimes, in the concepts that we're working with, we may be trying to determine whether something exists or not, whether maybe a value exists, without actually finding the value. In other words, can you tell me that there is a number that exists within a certain interval without necessarily telling me what that number is, but actually proving that it exists? I don't know if that makes sense or not. Let's look at this one and see if this works out. Use the intermediate value theorem to show that there is a root of the equation square root of x cubed minus or equals 1 minus x in the interval from 0 to 1. Now, first of all, just some quick notation or terminology. When we talk about a root of an equation, that's just another word for a solution to an equation. So our question is, we're trying to show that there is a solution to that equation in that interval between 0 and 1. Another word for those, we also call them zeros of a function. You may remember that from algebra. The root of an equation, the solution of an equation, the zero of a function, which corresponds to the x-intercept on the graph of that function. All right. So these two terms are related to each other in that the root of an equation is the same as the solution to the equation. We also say that the root of a function is the same as a zero of the function, which graphically corresponds to an x-intercept on the graph of the function, because that is a function, a value for x, a value for the input, that produces 0 as the output. Right? Again, that's an algebra review. So we're interested in, if I take then this equation and I'm looking for a root to that equation in a specific interval, here's how we can do it. Let's just rewrite the equation. Right, now, of course, first and foremost, you could try to solve the equation, right? Because we're asked to show that there's a solution there. You could try to solve the equation, but good luck with that. You look at the equation that you're working with there, and this is what I mean when I was talking earlier. Sometimes it may be more trouble than it's worth, or maybe not even possible. Like in this case, to solve the equation, but maybe we can show that there is a solution without actually finding the solution specifically, right? And so that's all we're asked to do here. We're just asked to show that there actually is a solution. We're not asked to find it. We just want to show that it exists, okay? So what I did first was I rewrote the equation. So this is another one of those cases where the ends justifies the means. It's like, well, why do that? Because now I can let that left side of that equation be our function f of x. And then what I'm looking for is there a value for x where that function is equal to 0? Is there a value for x that corresponds to an x-intercept on the graph of that function? Is there a value for x that produces 0 as the output of the function? Okay? So it makes it easier to work with. It also then allows us to use something like an IVT. Now, provided that we do have continuity over the interval, we can use the IVT. We said don't take that for granted. Is that function continuous on the interval from 0 to 1? Well, it has to do with the domain of the function. We said as long as whatever the domain of the function is, I see a radical function there. That was in our list. It's continuous over its domain. What's the domain of our square root function? We already said earlier the radicand cannot be negative, so in this case x cubed would have to be non-negative, or x would have to be non-negative, so 0 to infinity would be the domain of that function. I don't have any problems with this. It's all about that square root. So because of the square root, the domain of that function would be 0 to infinity, which of course includes 0 to 1. Including 0, right? So we do have continuity on that interval. And so we are asked to find a solution within the interval from 0 to 1. The first thing we have is continuity so that we can use the IVT. What's the second requirement for the IVT to hold true? The function values at each endpoint of the interval have to be different. So we look at f of a. A is our left endpoint of that interval, which is 0. F of 0, you plug that into that function, you've got 0 plus 0 minus 1, or negative 1. So f of 0 is negative 1, so that means on my graph I have a point at 0, negative 1. f of b, that's your right endpoint, which would be f of 1, the right side of right endpoint of the interval. And if I plug 1 into that function, I've got 1 minus 1, which is 0. Excuse me, 1 plus 1, which is 2, scratch that, minus 1 gives me 1. So f of 1 is 1 when I plug it into that function, so I have a point at 1, 1. Now here's why that issue of continuity was so important. Here's what I know about this function. And this is how the IVT works. See where I want to put this. Whatever the graph of this function looks like, we've just proven, or we've just shown, that there is a point at 0, negative 1 on the graph of that function. We've also shown that there is a point at 1, 1. And we also said that that function is continuous on this interval, which means if I'm going to draw the graph of this function between those 2 points, at some point what has to happen? At some point, I have to cross the x-axis, which means at some point there's an x-intercept, which means at some point there's a 0, which means at some point there's a root to that function between 0 and 1. That's why the continuity is so important, right? So here's the bottom line. Here's kind of this in a nutshell. Here's what I did. I took an equation. I said, let's see if let's prove that there's a root to the equation in the given interval. So what did I do? I rewrote the equation, simply setting it equal to 0, so that I can then use the left side of this as my function. And then we simply need to show that somewhere between 0 and 1, there's a function value that is equal to 0. So we plug in our endpoints. We plug in A and B, the endpoints of the interval. And what you want to see happen in order for this theorem to work, I want to see one of those values being positive, and I want to see one of these values being negative. Because we're trying to show that our function value is 0 somewhere in this interval, which means it would have to be between a positive and a negative number. Okay? And again, they all work the same. They follow exactly the same process, provided the requirements are met. So first of all, rewrite the equation, set it equal to 0. Second, let that be your function. Third, we need to guarantee continuity. All right, I think I overlooked that. So we at least need to qualify or justify that the function is continuous over the interval. If that's true, then if we should be able to evaluate the endpoints of our interval, plug in your A, plug in your B, and if one of those values is positive and the other is negative, then 0 has to fall between those two, because that's what we were trying to show, that the function was equal to 0 somewhere in that interval. So there's our f of A, there's our f of B. Our n value in this case is 0. So then I can say that there is a number c in the interval from 0 to 1 such that that f of c is equal to 0. And so I could then make the general statement back to the original equation. So I know that that function has a 0 in that interval, which means there is also a root to the equation in that interval. Because remember, this was the original question that we were trying to answer, so don't forget to go back and make a statement to that effect. This is showing me that there's a 0 of that function in the interval. So I then have to relate it back to the equation that we started with and say that that equation has a root. Okay, the IVT is a pretty neat little theorem. I think it makes perfect sense when you look at it, but as is true with a lot of this stuff, it's the execution, right? You have to follow the steps to actually prove or show that the statement is true. All right, that's it for that section. That is section 2.5.